All right, so let's talk about this matrix N. Okay, so it is a 2 by 2 matrix, 0, 0, 1, 0. Okay, so now this matrix is non-diagonalizable. Okay, how do we see that? Well, a couple of things. So, a couple of things to note. It says the fact that N is not the zero matrix means that it cannot be similar to the zero matrix, because the only thing similar to the zero matrix is, of course, the zero matrix. Also, hence, if N were to be similar to a diagonal matrix, for example, D, then D would have at least one non-zero entry on its diagonal, right? Since we know it can't be the zero matrix, so it has to have at least one non-zero entry along the diagonal. At least one. Okay? Now, the crucial point here is to notice that if we take powers of n, we get the zero matrix. In fact, n squared. N squared will give you the zero matrix. Okay, so why is that important? Well, think about it this way. This implies that for any map N, represented by the matrix N, with respect to some basis B to B, the composition of N by N, right? So if we have a mapping N and we compose it with itself, it gives us the zero map. And so this in turn implies that any matrix representing N, the function N, with respect to some basis B hat to B hat, has a square that is the zero matrix. But for any non-zero diagonal matrix D squared, right? So let's say we have some diagonal matrix D, right? And now we want to consider D squared. The entries of D squared are the squares of the entries of D, because if, again, this is diagonal, right? So if we look at D squared, all it's doing is it's taking the diagonal and squaring the diagonal entries. And so D squared cannot be the zero matrix. Thus, the matrix N is not diagonalizable. So not every similarity class contains a diagonal matrix. And so now we're going to characterize when a matrix is diagonalizable.